I've been spending the last few years developing new techniques to simplify and improve in situ skin temperature measurements. The conventional approach is to use a radiometer in the 9.6 to 11.5 micron range with a mirror in order to view two uh, internal black bodies, one at ambient and one at a hotter temperature, heated, that allows us to get the gain and the offset of the radiometer. And also the same radiometer and mirror combination is used to measure both the sea and the sky. Over the last couple of decades, commercially available radiometers have improved greatly in stability. And so my new approach is to take advantage of that stability and just do a simple 1-point calibration with an ambient temperature black body, which provides us with the offset. This eliminates the mirror, and if we use separate radiometers to measure the sea and sky. I'm also looking at the optimal spectral band technique, which uses a narrow band near the edge of the atmospheric transparent window, which can reduce uncertainty due to sky reflection and emissivity effects. And as I'll show here today, we may even be able to eliminate the sky measurement by modeling the atmospheric temperature and humidity by using air temperature and relative humidity measured on the ship. So I'm going to very briefly talk about the simplified calibration approach and then spend most of the time on the optimal spectral band preliminary results. On the left is the Rosser, which is a conventional instrument. We use a Rosser here as a reference standard. It has a radiometer and two internal black bodies and a scan mirror. The IRIS design is to use a comparable radiometer with a baffle block on the front here and a simple flat plate black body with a precision thermistor embedded in it. And that's attached to an actuator. So the black body rotates down in front of the radiometer periodically to do the offset calibration. Then we have a separate radiometer for the sky measurement that has a rain guard that prevents water from accumulating in the lens. We deployed two Rossers and two different versions of the IRIS. In 2022, on a cruise off of San Francisco, we used the standard wavelength band and then the optimal wavelength band. We use two Rossers because we want to be able to compare them with each other to understand, to quantify the uncertainty of the Rossers themselves. So that's plotted here where we plot the skin temperature from Rosser 3 versus Rosser 9. And you can see the average difference is 0.03 degrees, and the standard deviation is less than 1/10 of a degree. So we're using the Rossers here with an accuracy of plus or minus 0.1 degrees C, which is comparable to previous comparisons between a variety of instruments in the past. Now, if we do the same plot of the IRIS skin temperature using the standard band versus the skin temperature from the Rosser 9, you can see that the agreement is very good. The average, there's no mean offset, and the standard deviation is the same. So here we can conclude that the IRIS with the 1-point in situ cal has accuracy comparable to the Rosser. Now, the optimal spectral band technique is, as I said, intended to reduce the uncertainties associated with the emissivity and the sky radiance shown here in the radiative transfer equation. When you use a conventional band in the 8 to 14 micron transparent window, the range of the sky radiance or temperature is very large because these clouds are warm, they're on the order of the air temperature, and the sky is very cold because you see through the atmosphere to outer space. When we use a band that's narrow and close to the edge of the transparent window, then that absorptive band basically causes the atmosphere to look relatively opaque, and because the reflected sky radiance is just from a few kilometers from the ship, and it's dominated by the temperature and water vapor by the water vapor in the air. And so the sky radiance is relatively invariant because it's not affected by clouds very much. And that's illustrated in the time series of these temperatures from the experiment. The red is the air temperature, it was relatively constant. And then the green is the sky temperature from the optimal band, and the black is the sky temperature from the standard band. You can see that when it's cloudy, both radiometers measure a temperature that's very close to the air temperature. But when it's clear, you get a very large deviation in the standard band and a relatively small deviation in the optimal band. So now if we plot the skin temperature from the iris using this optimal band against, again, the skin temperature from roster number 9, you can see that the mean difference is, again, quite small, but our standard deviation has increased by about 75%. And I think this is probably due to the increased variance in the signal, due to the reduced signal caused by the narrow spectral band. This is the spectral response of the two instruments. The optimal band is narrower and a lower magnitude. But I think we can improve that and reduce the variance by using a larger aperture instrument. Our current instrument uses a 26 millimeter aperture, and it has a NEDT of 0.55 Kelvin. If we use the alternative larger lens on the KT-19, then the noise equivalent temperature difference is significantly reduced. So I think we can probably reduce this scatter by using a larger lens. Now, since we had radiosondes being launched during the experiment, we can look at the idea of modeling the sky temperature based on the sky radiance spectrum that can be obtained from ModTran software by initializing it with the radiosonde profiles. Here's an example of a profile where it's cloudy, where you see this very strong inversion in the temperature and the relative humidity. And here's a case where it's very clear and you see a relatively linear lapse rate in the temperature. So the radiance that we measure that then can be converted to the sky temperature is given by the integral of the weighted spectrum here, shown in this equation. And you can see this is the spectrum of the sky, and this is where the IR transparent window is, so we have very little radiance in that window. So the first thing we did then was to compute the sky temperature from the radiosonde data, and then and that's shown here. And you can see that in general, the modeled or the radiosondes, the sky temperature from the radiosondes follows the measured sky temperature quite well. So then you can imagine that we could do a linear fit to the profiles when it's clear, and then recompute the spectrum and estimate the temperature that way. And that's shown here in the purple diamonds, where now this is the sky temperature derived from ModTran doing a linear fit to each one of the radiosondes. Then if we want to just model the radiosonde based on temperature and relative humidity on the ship, we can take a constant slope, a constant lapse rate for all of the radiosondes and just initialize it at the beginning with the measurements from the ship, and that's shown here in in blue, where we see the sky temperature agreeing quite well. And so when we summarize that in this plot, here I'm going to plot the skin temperature from ModTran using T-sky from ModTran with these 3 different techniques versus the skin temperature using the measured sky temperature. And you can see that they agree quite well, and the statistics show that there's very little difference. So in conclusion, we've shown that the accuracy of the standard iris is comparable to the Rosser, and the optimal band technique shows promising results. And the next step is to reduce the variance by using a larger aperture.